The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
Okay, so last time we started talking about the internal motions of molecules, the vibrations and the rotations. And we talked about how the different ways in which a molecule can store energy were called modes, or sometimes called the degrees of freedom. And so in general here, if we've got a molecule that has n atoms, a molecule with n atoms has 3n degrees of freedom, or 3n modes. And we said last time that 3 of those 3n modes are always translational modes. We live in a three-dimensional universe, so there are 3 translational modes. 3 directions in which the molecule can travel, can move. And therefore, if we use 3 of these 3n modes for translation, then we have 3 minus 3 modes that are internal modes, internal degrees of freedom. All right? And that's what we really want to start looking at today. So, on the diagram here on the side, here's our n molecule. There are 3n total modes. I just said 3 of them were translational modes. Now, how do we separate those remaining modes between rotation and vibration? Well, the way we do it is this. If you've got a molecule that is linear, you always have 2 rotational modes. I'll show you that in a moment. Linear molecules always have 2 rotational modes. Nonlinear molecules have 3 rotational modes. Therefore, if we use, in a linear molecule, 3 of them for translation, 2 of them for rotation, the number of vibrational modes are what's left over. So for a linear molecule, we have 3n minus 5 vibrational modes. And that's for a linear molecule. If we've got a nonlinear molecule, well, since we've got 3 rotational modes in a nonlinear molecule, we have left over 3n minus 6 vibrational modes in a nonlinear molecule. Okay. So now let's take a look at this a little bit more in detail. Let's start with the nitrogen. 2 modes, or 2 atoms, 6 modes total, 3 translation, 2 rotational modes of nitrogen. What are those rotational modes? Well, here's our nitrogen. And one of those rotational modes is going to be rotation about an axis in the plane of this board. And it's rotation around this axis. That axis goes through the center of mass of that molecule. That's one of the rotational modes. Another rotational mode is rotation around an axis here that is perpendicular to the board. Right? This is another rotational mode. It's going to turn out that these 2 rotational modes are degenerate, meaning they're going to have the same frequency of rotation, they're going to have the same energy. Okay, we'll talk about that in a moment. What I want to point out here is that if you look at the axis here in the plane of the board that is along the bond axis, this, hey, you know what? This is not a rotational mode, all right, because there's symmetry, cylindrical symmetry around that bond axis. It has no meaning, rotation, around that bond axis. The molecule looks the same for all of the angles from 0 to 360 degrees. That is not a rotational mode. All right, so linear molecules, diatomics, you have two rotational modes. They're going to turn out to be degenerate, as we're going to see. Okay, and then our table over there says for nitrogen, well, we ought to have one vibrational mode. And we do. That one vibrational mode here is the nitrogen-nitrogen stretch. It's a stretch mode. Right? We said last time that these bonds function like a spring. The molecule can stretch, the molecule can compress. We're going to look at that in more detail in just a moment. Okay, so next, in our table over here, let's look at CO2. CO2 has 3 atoms, 9 total modes. 3 of them are translation. But now CO2, even though it has 3 atoms in it, it is a linear molecule. So it has only 2 rotational modes. Let's look at and see what those 2 rotational modes are. All right, one of those rotational modes is, again, rotation around an axis in the plane of the board here, right, around the center of mass of that molecule. That's one rotational mode. The other rotational mode is around an axis perpendicular to the board here. That's the second rotational mode. These 2 modes are going to be degenerate. They're degenerate because they're actually the same motion, just in a different plane. Right? These are degenerate. And then again, just to emphasize, if you think that you've got a rotation here along that linear bond axis, well, the answer is no. This is not a rotational mode. All right, so we have 2 rotational modes for CO2. Okay, and now what does our table say in terms of vibration? Well, in terms of vibration, for a linear molecule, 3n minus 5, we have used now 5 modes. We have got 4 left, 3n minus 5. So what are those modes? Okay, so one of those modes here, right, one of these modes is what we call a symmetric stretch. So a symmetric stretch means that this oxygen and this oxygen are simultaneously stretching or are simultaneously compressing. So if my body is the carbon and my arms are the oxygen, right, a symmetric stretch is the oxygen's both moving in or both moving out. That is one vibrational mode, this symmetric stretch. Okay? That's one vibrational mode. What's another vibrational mode? Well, if you have a symmetric stretch, it must mean you have an anti-symmetric stretch. All right, in this case, we've got one oxygen moving out while the other oxygen is moving in, and this carbon is kind of moving in like that too. Or this one's moving in, this one's moving in, this one's moving out. That's the anti-symmetric stretch. So if my body's the carbon and my arms are the oxygen, right, this is the anti-symmetric stretch with the carbon moving just a little bit to the side too. Okay? The anti-symmetric stretch. Another mode. These 2 modes are not degenerate. They have different frequencies. They have different energies. We'll see that in a moment. Okay. Complicated board here. All right. What are the other modes? Well, the other modes are a bending mode. All right? So what can happen is that this oxygen and this oxygen can move in, and this carbon will kind of move out, or, of course, the other way here. These go like that, this goes like that, or that goes like that. This is a bending vibration. All right? So, again, you know, if I'm, my body's the carbon, and these are the oxygens, right, the bending vibration looks like this. Right? That's the bending vibration. All right, so that's a bending vibration now. However, you could also imagine that you have a bend in another plane. In other words, you can imagine that these two oxygens here are coming out at you or going in at you. All right? And so, in other words, if I'm the carbon, these are the oxygens, we also have a bend like this. Right? Okay. So these two bending vibrations are degenerate. These are 4 different vibrations. They're the 4 vibrational modes. 2 bending, 1 symmetric stretch, and the other the anti-symmetric stretch. Okay, that's what we got in CO2. Now, what about another molecule? How about water? Water, we got 3 atoms. So again, 9 total modes. 3 of them are translation, but now water is not a linear molecule. So we're going to have 3 rotational modes in the case of water. Let's look at what those 3 rotational modes ought to look like. All right, so here's our water molecule. All right. One of those rotations is, again, a rotation around an axis here in the plane of the board. All right. So that's one rotational mode. So if I'm the oxygen and my hands are the hydrogen, this is a rotational mode. You got that? Okay. And then another rotational mode here. If can be a rotation around here, the center of the mass, centered on the oxygen here, axis perpendicular to the plane of the board. Hey, this is that rotation. All right. And I'm sorry, but I can't do cartwheels. That's one rotational mode. And then a final rotational mode involves rotation now around this axis. Right? It's an axis perpendicular to this one, but in the plane of the board. Right? And this is a rotational mode. All right? So we got 3 rotational modes. This one requires me to do some flips, which I'm also not going to do. But each one of these modes has a different frequency, has a different energy. All right? And you can see we got 3 of them now because we no longer have a linear molecule. We got 3 rotational modes. Okay. Now, what about the vibrations for water? Well, you can see from our graph up here that 3n minus 6, in this case for water, is going to be 3 vibrational modes. So let's look at that. All right. One of those, I'm always losing my chalk here. Okay, one of those vibrational modes is a symmetric stretch again, right? The hydrogens moving in or both moving out at the same time. You know, a picture of the symmetric stretch is, again, I'm the oxygen, arms are the hydrogen. This is the symmetric stretch, right? Okay. So, symmetric stretch. And then if there's a symmetric stretch, there's going to be an anti-symmetric stretch. So what that means is one of the hydrogens moving in and the other one moving out, or this way. All right? So, of course, a picture for that is, this kind of motion. You get the idea. Antisymmetric stretch. Okay, and then finally, we have a bending mode. All right? A bending mode meaning these hydrogens moving this way, right? Or those hydrogens moving that way. And, of course, a picture for that is this, right? That's a bending mode for the hydrogens. Okay, so we got three vibrational modes for the hydrogen. Now, we're going to look at some of the principles behind these internal degrees of freedom. But, of course, the other reason for telling you about this, did you have a question?
Yeah, why can the hydrogen not bend in and out of the plane?
It can, but it's not a separate mode, okay? That's correct. That's right. It looks like a rotation, actually. That's absolutely correct. Okay. So the other reason for talking about this is to tell you that each one of these vibrations or rotations occurs at a frequency, at an energy that is characteristic of the molecule. So if we had a way to actually measure the frequency of these vibrations or the frequencies of the rotations, well then we got a great tool for identifying what kind of molecule that we have. All right, so analytically this is a wonderful technique for identifying ultimately the molecule that you have, if you can measure those frequencies of vibration or rotation, and we're going to do that in just a moment. Okay, but what we also have to understand before we go and measure these frequencies is we have to understand that the energies with which a molecule vibrate or rotate, hey, you know what? Those energies are quantized. All right, so that's what we got to spend some time thinking about right now. So let's do that. And I'm actually going to use the center board here. And we're going to start with vibration. And to illustrate this, I'm going to draw one of these energies of interaction again. One of these curves that we've been talking about. All right. So, and I'm going to set my zero of energy at the dissociated atom limit. So I'm going to talk about H plus Cl. All right. And of course, right here, we talked about this being the equilibrium bond length, R sub E, for the HCl molecule. All right. So that's the energy of interaction. Now, I'm going to now draw in the ground vibrational state of HCl. The ground vibrational state, I'm going to represent it as a line. It's going to be the energy. All right? There's the ground vibrational state of HCl. The ground vibrational state, that energy is characterized by a quantum number. The quantum number is the vibrational quantum number. For the ground vibrational state, the vibrational quantum number is V equals 0. Okay? What this line means, what it represents, is the ground vibrational energy. It also represents the extent to which the molecule's bond stretches and compresses. The bottom line here is that the bond stretches up to here, right? The intersection of this line with the interaction energy here represents the maximum distance of the bond the maximum bond length, the most that the bond stretches. You know, R is going this way. The intersection of this energy with this curve represents the closest that the two nuclei get. So this represents the most that the molecule has compressed. This is the smallest value of R. All right? That's what that diagram represents. So if you start out here with an HCl molecule at the equilibrium bond length right here, what happens is that the HCl will stretch, and it'll stretch to this position. Right? So this is an exaggeration. This is how much it stretches. And then it comes back, goes through the equilibrium position, and over here, this is another exaggeration. This is how close they get to each other. This is how much they compress. All right? This point is often called the inner turning point. Inner because it's the smallest bond distance. This is often called the outer turning point because it's the larger bond distance. It's outer because it's at this distance now that the bond turns around and begins to compress. All right, so this molecule, this HCl molecule here, is vibrating. Equilibrium position, then it goes to the maximum extension, comes back through the equilibrium position, and then goes to the maximum compression, comes back to the equilibrium position. All right? That is what this line literally represents. It's also the energy, which I'll explain a little bit more in just a moment. All right? So this molecule's vibrating from here to here to here and back and forth. Okay? Okay. Now, what I also want to point out to you is something that I've been kind of misleading you about for the last few weeks. And that is that this molecule is not sitting in the bottom of this well. Remember that when we were drawing bond dissociation energies, remember I was drawing it from the bottom of this well to the dissociated atom limit. I told you this was delta E sub D. Okay? Well, the bottom line is that that's not really correct. And the reason is because the molecule is never really sitting at the bottom of this well. It is sitting this much above. It is sitting at the V equals 0 state. It is not sitting at the bottom of the well. If it were sitting at the bottom of the well, it wouldn't be vibrating. If it's not vibrating, it will violate the uncertainty principle. Something we didn't talk about, but the bottom line is that it can't sit at the bottom of the well. It is always vibrating by about this much energy. Okay? So when you measure, when you have an experimentally determined dissociation energy for the bond energy, the experimentally determined energy is actually the energy from this level, from V equals 0 up to this dissociation limit. This is the experimental bond energy, right? Because if you're going to measure a bond energy in the laboratory, well, you can only measure it from the lowest level at which that molecule can possibly be at. It's not at the bottom of the well. All right? The difference between where this level is and the bottom of the well actually has a name. That difference is called the 0 point energy. And I'll explain that in a moment when we look at the energies a little more carefully. Okay? Now, just for completeness And this isn't something that you have to know, but just for completeness, let me tell you what the nomenclature usually is here for these well depths. The nomenclature from the bottom of the well to here, which is not experimentally measured, the nomenclature usually is D sub E, dissociation sub E. All right. From, yeah, we could put those on. Okay. From the V equals 0 level, right, to the dissociation limit, that energy here is D sub 0. Okay, you don't have to know these, but I just want to tell you when you see that. All right, so all dissociation energies, experimentally dissociation energies, experimentally measured, are measured from here to here because that's the lowest energy the molecule can have, is being in the V equals 0 ground vibrational state. Okay, well now let's take a look at the energies a little more carefully. Okay, so here's our favorite diagram again, our intermolecular interaction potential. This is HCl, so here's the dissociated atom limit. Here, this is V equals 0, right in there. V equals 0 right here. Okay. Now, there is an excited state for the HCl or for any molecule. V equal 1, that's the first vibrationally excited state. V equal 2 is the second vibrationally excited state. V equal 3 is the third. V equal 4 is the fourth. V equal 5 is the fifth. Third, fourth, fifth, right. Okay. All right? These are the allowed vibrational energies. So in other words, the molecule can vibrate with this energy, or this energy, or this energy, but not some arbitrary energy like right in here or like right in there. These are the allowed vibrational states. And we have a nice analytical expression to describe those energies. That analytical expression's right here, right? That energy is H times nu. Let me get this other pointer. That energy here is H. None of my pointers are doing my thing. That energy is H times nu times that vibrational quantum number plus 1/2. All right? So V is that vibrational quantum number. This nu here, hey, that's the fundamental frequency. The fundamental frequency is the frequency with which the molecule vibrates. It is the frequency with which that molecule stretches, comes back to the equilibrium position, compresses, comes back to the equilibrium position. It is the number of cycles per second that molecule makes. Okay? So nu is the number of cycles here that the molecule in V equals 0 makes per second. You know, stretches, compresses, and back to the equilibrium position. Notice it is also the vibrational frequency of V equal 1. The vibrational frequency doesn't depend on the vibrational quantum number. It doesn't, you see no dependence of the vibrational quantum number on the frequency. Right? V equal 2 vibrates with the same frequency. V equal 3, V equal 4, V equal 5. Hey, all of these states have the same nu here, have the same fundamental frequency. Hey, what does that mean? That looks a little strange in the sense that if you have a molecule in V equals 0, the number of cycles per second that it makes is the same as a molecule in V equal 5, right? Well, but you can see that in V equal 5, the molecule has to stretch further and it has to compress further. It's got to travel more distance. And so if it's got to travel more distance, but it still makes the number of cycles per second, it still carries out the number of cycles per unit time the same as V equals 0, well then, hey, it must mean that the molecule in V equal 5 is moving more quickly, is moving faster. Hey, and that is what that means, right? The energy of this state is higher. It is moving faster, right? But it's moving with the same frequency, mu. That's the fundamental frequency. Okay? Okay, that fundamental frequency, of course, is in hertz, our unit for all frequencies here. Now, I drew on the board, I said this energy from the bottom of the well to V equals 0, I call that the 0 point energy. That's what it is. But numerically, what that energy is 1/2 h nu. Stick in V equals 0, you get 1/2 h nu. So this energy here is measured from the bottom of this well. All right, that's important that you understand where this energy is measured from. It's measured from the bottom of this well. V equal 1, you put in V equal 1 here, you get 3/2 h nu. V equal 2, you get 5/2 h nu. V equal 3, whoops, what happened? No more. you get 7/2 h nu. All right? Hey, the other thing to notice is that these states are equally spaced. The energy spacing between any two adjacent states is h times nu.
It's drawn slightly different in our notes. It doesn't start from the bottom of the well.
That is incorrect. What I'm drawing here is right. I'm sorry about that. Okay, sorry. Okay, 1/2 h nu is from the bottom of the well to V equals 0. Okay. I think I know what happened. All right, what I've shown you here is correct. What's in your notes is printed incorrectly. All right, so you should make note of that and change that. Okay, so now suppose we have a molecule in the V equals 0 state where the energy is 1/2 h nu. That molecule can be excited to the V equal 1 state. That molecule in V equals 0 is still vibrating, but we can make it vibrate even faster, right? With more energy. Same cycles per second, but with more energy, by promoting it to V equal 1. We can do that if the molecule absorbs a photon, right? And the energy of that photon has to be equal to the difference in the energies of these two states. So if the final energy here of the V equal 1 state, that's the final state, if that energy is 3/2 h nu, and the energy of the initial state was 1/2 h nu, then the difference in energy between the states is h nu. So we have to have a photon that has exactly this energy difference, delta E. That delta E then has to be gotten by a photon with a frequency equal to nu. Hey, and the frequency of that photon that's going to make that transition is actually also the vibration, is also the fundamental frequency of the molecule, right? Hey, we're lucky on this one. Nu here is delta E over h. We have to have a photon with that frequency for the molecule to be promoted from V equals 0 to V equal 1. How do we know what that is? Well, we do an experiment. We do an infrared spectroscopy type of experiment. The difference in the energies between states, vibrational states, that difference in the energies is in the infrared range of the electromagnetic spectrum. And so we're going to use infrared radiation. So we have some source of infrared radiation, puts out all different frequencies in the infrared, and then we send it through a monochromator. The monochromator disperses that radiation in space, and it allows, only a certain frequency of radiation to come right through the slits and out into our sample. Okay? So it's like you had the diffraction glasses where we disperse the radiation in space. Well, this is what a monochromator is essentially the same thing. There's a diffraction grating in it, and it allows out of the front end only radiation of a certain frequency to come out, and we can adjust what that radiation is or what frequency that radiation has. We then allow it to pass through our sample, say HCl. And then there's a photodetector over here, some kind of photomultiplier. And what will happen is that if this molecule is going to absorb frequency of that radiation, well, then the number of photons reaching the photodetector is going to go down. So if the frequency doesn't match the frequency of the vibration of HCl, well, the photons go right through onto the detector. But if it matches, then the molecule absorbs those photons and they never make it to the detector. All right, so a plot looks like this. This is the intensity at the detector versus the frequency of the radiation. The intensity will be high, but now it's some frequency, which will turn out to be the vibrational frequency of the molecule. The intensity goes down low. And then as you go to higher frequency, the intensity comes back up. Right here, the molecule has made the transition from V equals 0 to V equal 1 because the frequency of that photon matches the energy difference between V equals 0 and V equal 1 divided by H. It also happens to be the fundamental frequency of the molecule, all right, for HCl. So that's how we know what those fundamental frequencies are. So let's now look at what those energies are. All right? So we've gone from V equals 0 to V equal 1. Delta E equal H nu. We just measured nu as 8.6 times 10 to the 13th inverse seconds. Multiply it by H, that's going to give us delta E. The difference in energy between the two states is 5.7 times 10 to the minus 20 joules. If I turn that into kilojoules per mole, hey, that's 35 kilojoules per mole. All right? That's the energy difference from here to here, about 35 kilojoules per mole. How strong is the HCl bond? Well, the HCl bond from here to here is about 420 kilojoules per mole. So this is about a tenth, right? A little bit less than a tenth of the total bond strength for HCl. All right, so if we make it vibrate, we're not going to make that bond break. It's an order of magnitude less energy here than what you need to break that bond. Okay, now, here's something that's a little confusing. And that is that these frequencies, these fundamental frequencies, it turns out that we actually use a different convention to label them, a different units. We don't use hertz very often to talk about the frequencies or the fundamental frequencies of molecules. We use something called a wave number instead of hertz. And a wave number is an inverse centimeter. It's centimeter to the 1/2 power, to the minus 1 power. The symbol for a wave number is a frequency sign with a bar on top of it. That's a wave number. Okay? How do we get a wave number? Well, we get a wave number by taking the frequency in hertz, inverse seconds, and dividing it by the speed of light. But the speed of light, of course, has to be in centimeters per second. the seconds cancel, and what we have then is left is inverse centimeters. So for example, if the frequency, the fundamental frequency of HCl was 8.6 times 10 to the 13th hertz, we divide that by the speed of light in centimeters per second, and the wave numbers, or the fundamental frequency in wave numbers, then is 2,886 wave numbers for HCl. Okay? So these are the common units that are used to talk about the fundamental frequencies of vibrational frequencies of molecules. And these are the common numbers used to discuss infrared spectra of molecules, this unit of a wave number. It's a non-SI unit. All right, so in other words, what you'll often see is an infrared spectrum, intensity at the photodiode now versus wave number, and right at 2,886 wave numbers, that's the fundamental frequency in wave numbers. That's where the molecule makes the transition from V equals 0 to V equal 1. Okay. So now the question is, what determines the frequency of the vibration of a molecule? Well, what determines the frequency of that vibration, and here I've now gone back to frequency because I'm writing it in terms of some other parameters. What determines that frequency are two parameters. One is the force constant K, and the other is the mass. Now, what I've got here is the reduced mass. I'll explain that to you in just a moment, but this is essentially the mass. So the frequency is given by 1 over 2 pi times the square root of this K, the force constant, over the mass. K, that force constant, is a measure of the stiffness of the spring. So in other words, if you've got a very stiff spring, K is very large. That is, you need a lot of force to pull that spring apart, a lot of force to compress that spring. So a large K means you've got a very stiff spring. If you have a small K, that means you have a very weak spring. It doesn't take very much force to pull that spring, to stretch that spring, or to compress that spring. Okay? So K is a measure of the stiffness of the spring. It also tells us something about the shape of the interaction energy. In other words, what K actually tells us here is kind of the width of this well. Here's my interaction energy potential well. If you have a very narrow width, this is a large K. If you have a very broad width here, this is a small K. All right? So K, the force constant, tells us about the shape here of this well. Very narrow well, large K. Very small, very broad K, very broad well, small K. Okay? Now, I think that maybe you've seen this before, right? In 801, have you done the harmonic oscillator yet? No? Yes? Some yes, some no. Mostly no, it sounds to me. All right. This expression here for the frequency, you're going to see in 801 sometime. It comes from the harmonic oscillator model. So you'll remember that you've seen this before. Okay? Those of you who have know what I'm talking about. Those of you who haven't, just remember you're going to see this very soon once again. Okay, now the other parameter here that's important is this mu here, this reduced mass. What the reduced mass is essentially the mass. Now, if you had already done this in 801, what you're going to look at is a mass on the end of a spring attached to a wall. So there'll be a wall, and then you'll see a spring, and then there'll be some mass m. So when you do this problem as a harmonic oscillator, you're going to write nu here as k over the mass, this mass right there. All right? But in this example, this mass here is the only body that's moving. Your wall is still. But in the case of a molecule, both atoms are moving. Okay? Both are moving. So what mass do we use? Well, the fact that both are moving means we got a two-body problem. And we're going to have to change the coordinate system to take into account that both masses are moving. We can do that easily. And doing that easily involves using something called the reduced mass. The reduced mass takes a two-body problem and reduces it to a single body, where the single body is this fictitious body with a mass given by the reduced mass. All right? It's exact. I didn't make any approximations here. All right? Okay, but the bottom line is that this reduced mass is simply the mass of one atom times the mass of the other divided by the sum of the two masses. Okay? And sometimes a useful approximation is when one of the masses is much lower than the other mass. So when M1 here is smaller than M2, well, you can see in that case, if M1 is very small compared to M2, we're going to treat it like a 0. And then these two M's are going to cancel. You can see the reduced mass is roughly equivalent to the mass of the smaller body. All right? Sometimes I'll ask you to use that approximation. Other times I'll ask you to calculate the reduced mass. Okay, so let's look at some frequencies for some molecules here. I've got an array of molecules. All of them roughly have the same force constant. So I'm going to look at the mass dependence on the fundamental frequency. I've got the frequencies written both in terms of wave numbers and hertz. First thing I want you to notice is the fundamental frequency for hydrogen. 4,159 wave numbers. Hey, that is the highest vibrational frequency that we know about. Why is it so high? Well, because those two hydrogens are so light. And the mass is in the denominator of that force constant, of that fundamental frequency, right? So if it's in the denominator, it's small. The fundamental frequency is going to be high. Then look at these molecules, HCl, HBr, HI. Well, in this case here, it's all a hydrogen bonded to a halogen. For the most part, the reduced mass of these three molecules is that of hydrogen. If that's of hydrogen, since that's in the denominator for the expression for the frequency, well, the frequencies are going to be high in general, and they are, right? 2,886, 2,559, not as high as molecular hydrogen, but still pretty high. And then we look at these three molecules, chlorine, bromine, iodine. Hey, both particles, very heavy. All right, the reduced mass is large. Look at what happened to the frequency here. The frequency really has gone down. All right, much lower than it was for HCl, HBr, or H2. So that's one parameter. The other parameter, of course, is the force constant. So here are molecules, set of molecules which have all roughly the same reduced mass, fluorine, oxygen, NO. And I've plotted, or I've written down their frequencies, both in wave numbers and hertz. For molecular fluorine, which has a single bond, hey, that frequency here is pretty low, 892 wave numbers. It's pretty low. This is a single bond. That single bond is easy to stretch. It's not very stiff. It is a loose bond, so to speak. But now look at oxygen and NO. Oxygen and NO have double bonds. Double bonds are stiffer. If they're stiffer, K is larger, the frequency, the fundamental frequency is higher. Then we look at CO and nitrogen. They have triple bonds. Triple bonds are even stiffer. Stiffer bonds, larger K, higher fundamental frequency. All right? So that's those two parameters that dictate the frequency of vibration. All right, we'll do rotation on Wednesday. See you then.